These are the slides pertaining to experimental error, which is covered in chapters 5 through 6 of your textbook. In order to understand experimental error, we have to understand the difference between accuracy and precision. Accuracy is a concept that measures the closeness of the average sample to the actual value. And so we'd see that if we have an accurate value, our average is always going to be very much on target. So we're going to see if a value is accurate. In each of these situations, the points are centered around the bullseye of this target. Now, precision is another concept where it talks about how much the points are spread apart, how much deviation there is in individual measurements. And so we might have a measurement that's accurate and precise, where the accuracy says that we're on target and precision means that all the points are spaced closely together. Whereas we could have a measurement that's accurate and not precise, where everything is averaged out right around the center, but we're spread out more than we'd like to be. We, of course, can also have things that are not accurate but precise. So we might have points that are spaced very close together but are consistently wrong. Or we might have something that's both accurate, not accurate and not precise, which of course would be a problem. Now this comes into play in a lot of our measurements. We might have something that's accurate and precise if we're doing the right measurement techniques and we're using the right tools. But say with a micropipetter, we use something that's a little bit too big for the volume that we want to measure. It might be fairly accurate, but it might not be very precise because it's made for a larger volume. Or we might consistently push down all the way past the first point of resistance on an auto pipette and then pull up all the way. We would consistently measure out too much volume, so it wouldn't be accurate, but it'd still probably be precise, unless of course we used, again, a micropipette that's much too large, in which case it'd be not accurate or precise. We could also think about similar concepts with an analytical balance for illustration. So an analytical balance that is a lot of decimal places would be very precise. Now it will also be accurate if we make sure that it's zeroed out and that we're using it properly, that it's balanced properly. It would not be precise if we used an organic lab scale. That doesn't have the same type of precision, but it's probably pretty accurate. Likewise, if we forget to tare our balance, regardless of whether it's an organic balance or an analytical balance, we'd see that we are not going to be accurate. We'd have a systematic error there. So we have lots of different concepts that refer to accuracy or precision that we have defined metrics for. So the first concept that I want to introduce is the concept of absolute error. Absolute error is a measurement of the difference between the mean values and the accepted mean. So we'd have each individual value minus the accepted mean. That's going to tell us the error for that measurement. Now notice, because we're subtracting the same types of measurements from each other, if we're measuring mils, the absolute error is in mils. If we're measuring grams, the absolute error is in grams. And so we're always going to have the same unit for absolute error as our measurement. Our relative error is going to be normalized for the scale of that measurement. So if we're measuring a large volume of something, it might not matter if we have a 1 mil error, whereas if we're measuring a small value of, or a small volume of something, a 1 mil error would be pretty significant. So we define that by taking the absolute error, maybe in mils, and dividing it by the accepted mean value for that. And so notice then that the units would cancel out, and so this would be a unitless. Oftentimes we express it as a percent. Now, accuracy also is involved with the concept of systematic error. Systematic errors are usually the avoidable errors. They're when we have a predictable one-directional type of bias to our results. So it might be like we were talking about before, where we're always over pipetting, or it might be that we're always rounding the wrong way. It might be that we have something on the scale that we didn't expect. Those are all examples of systematic error. We'll go into more detail on systematic error coming up. Gross error are like huge mistakes. Gross error is like, oh, I just completely forgot to drop a decimal place when I did a calculation, and now I've measured out 10 times too much. And so those would definitely be accuracy problems. And bias is when you, whether you know it or not, consistently make changes to your measurement that that result in a one-sided effect on your measurements. So like if you're always looking down at the meniscus from above, you're always going to get parallax error in the same direction. Or if you're always rounding up and never rounding down, you're always going to get a rounding error in the same direction. That would be affecting accuracy, and it would be due to personal bias. Now we can also have things that affect the precision. So one of the concepts related to precision is the deviation from the mean. So that's for an individual measurement. We compare that to the mean, and the larger the absolute value of the difference is, the larger that deviation is. We use that deviation in term to define a concept called variance. Variance is going to be equal to the sum of all deviations for all values in a sample divided by n minus 1, where n is the number of samples. Now notice this is actually true for samples, but it's not actually true for a population. We'll define this population variance differently, and we'll talk about it. That's why there's a star there. We also can define a standard deviation. Standard deviation squared is going to be equal to the variance. So if you want to find standard deviation from the variance, you just take the square root. That's actually much more commonly used because it's going to be on the same scale and same units as the types of measurements that we're doing. And just like we can have a relative error, we can also talk about a relative standard deviation. So we take our standard deviation and then divide it by the mean of values, and that gives us an idea of what the error is relative to the scale that we're working on. We can also talk about coefficient of variation. That's the relative error described as a percent. So it's really the same type of measurement as relative standard deviation, but it's now multiplied by 100% to express as a percent. All of these are really things that we consider under the category of random error. So these are the types of things that we try to reduce as much as possible, but to some extent we can't completely avoid. So we try to reduce the scale of them, but there will always be random error possible. We can also talk about the range, which refers to precision as well. It's talking about how wide the points are spread out from each other. We also call this concept spread. We use the variable w, and we say that the maximum value minus the minimum value are going to equal the range or spread. So obviously the larger range you have, the less tightly packed your points are, and the less precise they are. We tend to talk about two types of error more than any others, two archetypes of error really. One of those is systematic error, and that's the type of error that's dealt with in Chapter 5. Our systematic error is always determinate. So there's always a value to that. It's not going to be something that's variable. It's predictable, it's reproducible. So if you're always pipetting the same way, you're going to end up having the same type of predictable over pipetting. It's really bad. If you have systematic error that's left in your measurements, that's something that you should have fixed, and it's not really acceptable. So we have to figure out how to remove systematic error from our measurements. Some of the sources of systematic error include miscalibration. So like if we didn't calibrate correctly, if we didn't correct for certain factors. So if in some types of measurements we'll get interferences that we really need to remove. If we didn't do that, that will be a problem for us. We also end up having electronic drift. So we might start out with one intensity of light, but if we don't correct for the fact that it's started to dim or brighten over time, then we end up having a systematic error as well. So those are some common ways that we see that. In Chapter 6, we deal with random error instead of systematic error. Random error, unlike systematic error, is indeterminate. That means we don't really know what type of value it is. It could be up or down. It's not always in the same direction. It could be a different magnitude all the time, and we can't ever reproduce it. We're always going to have some random error in our measurements. That's just how measurements are. That means we're always going to have some uncertainty with our measurements. Some of the sources are things like sensitivity. So we need to have a scale that's to the, or whatever measurement tool we have that's to the right sensitivity to make sure that we reduce that. Obviously, when we're doing bigger masses, we don't need a sensitive scale. When we do smaller masses, we need a much more sensitive scale. Otherwise, the relative error gets really high. We also can have variable environmental factors affecting this. So like if the wind blows just a little bit over the scale, it might actually lift up the scale or push down the scale depending on how the wind is blowing. Or we might have electronic noise. So we can have random surges or sparse points in electricity, and that can affect a lot of our electronic data. And a lot of our instruments are electronic now. So to kind of show you how this plays out, you might remember from earlier slides in Chapter 2, we looked at how many samples, or Chapter 1 actually, we looked at how many samples were needed to get a good distribution of data that accurately represented the mean. And so here is one such randomly distributed set of data. Notice that we're going to have a distribution around a mean, and we're not always going to have the exact same points in the exact same place. We loaded this up a couple of different times, and we were able to see that it changed significantly where the mean was, and it also changed the spread of the points and the shape of that curve. Of course, the more values you add, so notice this is the same calculation, but now with many, many more points, the closer we're going to get to an actual true measurement. So we can take a lot of measurements, and then we can help to reduce the effect of random error. So let's hone in a little bit more on systematic errors. We split these up into 3 categories. Instrumental error. One of the best ways to deal with that is to just make sure that we calibrate the instrument or remove whatever interferences might be affecting our sample. We can also take blank samples. That's a sample that has everything but the analyte that we want to measure, and we can normalize the instrument with this. That's why oftentimes when we do UV vis measurements, we'll first take a blank measurement, and then we'll take our actual measurement. That allows us to zero out all the other types of interferences we might have seen with that instrument. We can have method error. This is really difficult to detect, but it's it's easiest to deal with if we have known errors with a method. So if we know, like if we're titrating, every time we titrate, in order to get that color change, we actually have to change the protonation of an indicator, and the indicator needs a certain amount of additional base past the endpoint in order for us to get the value right. We can blank titrate, so we can titrate just the indicator with no sample, but the same volume, and that can be a good way for controlling that, but we need to know some of those errors to deal with them. One way that you can identify errors if you don't know that you have an error is by using a standard reference material, just to validate your method, or you can send out your samples for independent analysis to see if anybody else gets a different result. We'll talk about how we deal statistically with those differences from different types of analysis in the next chapter, in Chapter 7. We can also have systematic errors from personal error, so things like gross error would fall in that category. Also bias would fall into that category, and so of course this is the one that we should most avoid outright, whereas the others are things that we correct for. Now, in our systematic errors, we could have constant errors. That's the same absolute error, regardless of sample size. These are actually fairly easy to deal with. If we have a systematic error that isn't something that we could just remove, like this titration extra volume that we need, we could increase the sample size in order to decrease the relative error. So the relative error is the error, again, relative to the value of the mean. If we increase that value of the mean by increasing sample size, we're going to decrease the relative error. And so that's an easy error to deal with. If we have proportional error, though, it's always going to have the same relative error no matter what the sample size is. And so there we actually have to remove the source of the error in order to get better data. When we are dealing with random error instead of systematic error, now we're going to have random distributions of data across a mean. And so we have what's called the standard normal curve, a Gaussian curve. This curve would be a good metric that kind of gives you an idea of what the shape of a Gaussian or a standard normal curve is. Notice that points are equally distributed on both sides of this curve. Notice we have a smooth curve all the way through, and that generally comes when we have a lot of data points. When we have just a few data points, we have a lot of variability in that data. So in this example, we have a different shape for our curve because we don't have quite enough data points. In this example, we had 32 data points. In this example, we had 800 something. So notice that between these two sets of samples that are defined by the same population, the smaller sample is going to have a different mean and a different standard deviation than the larger sample. We call the total set of all possible samples the population, and then we call the mean of that the true mean. We express it as mu instead of x bar because we're saying that that is the value that we accept, and we say that the standard deviation is going to be a sigma as shown below instead of an s. Now, that doesn't mean that we couldn't have error in the population as well. You know, all of those population results come from measurements, but we're able to get a much more accurate result the more measurements we take and eventually arrive at a consensus for the true result. Of course, I could improve this data even more by changing this 800 to 800,000, but at some point the effect of that is minimal. So notice we have a mean here of 4.73 for the population. We have a mean here for the sample. The mean for the population is more accurate, and the mean for the standard deviation for the population is also going to be more accurate. It's also going to tend to be a little bit more precise. We're going to be able to distribute those points a little bit more predictably with more points. Notice also that I put in equations for the standard deviation of a sample and of a population. I assume that you remember the calculations for mean, and those don't change between sample and population. But there is a difference here between the standard deviation with a sample and with a population, not just the variables we use. So in both cases, we're going to sum up all of the individual deviations, square them, and then divide. But in this example of a sample, we're going to divide by n minus 1. We have to deal with the extra degrees of freedom that we have removed by taking a sample rather than taking the whole population. So we end up taking n minus 1 as a better estimate of the degrees of freedom that we are going to normalize our standard deviation with. Whereas when we have the whole population, we actually have better data, and so then we can just use n. Now notice that the whole population is going to be a lot of points. It doesn't actually make that much difference, but it is better to use n instead of n minus 1 when we're dealing with a population. So suppose we take a sample. Of course, each individual value in that sample is going to have some deviation from the mean, and we can predict it, and we know this. But each one of our means is also going to have a predictable distribution around the actual value. We call this distribution the standard error of the mean. So we can predict on average how far our mean is going to be from the actual value dependent on sample size. So we say our standard error of the mean is Sm. We're going to say that we have our standard deviation of the sample divided by the square root of n is going to tell us on average how far off that mean is. Of course, n is the number of samples. So the question then becomes, if we want to try to reduce the error in any one of our samples of measurements, right? We want it to get as close to the mean as possible. We want that Sm value very low. Is it better to take more samples to increase this n? So again, here. Or is it better to increase precision, so decrease this s? So let's work out some of the math. So for example, if we increase precision tenfold, we'd essentially have s divided by 10 for our standard deviation. This could happen if we, say, use a more accurate scale. If we use a scale that has one more decimal place, we can increase that precision tenfold, and now we're going to end up with a value of Sm that is s over 10 square root n instead of our value of s over square root n. So that's better. It's better by tenfold. If we instead try to just increase the value of Sm, or sorry, increase the accuracy, decrease the value of Sm by increasing the number of samples, we would multiply by 10, but the 10 would go under here with the n, which means that our actual improvement is only on square root of 10, not actual 10. So we end up having a much lower result if we try to increase sampling. It's much better to increase precision by the same amount. So we're going to do everything that we can to take as precise of measurements as possible, because that means we'll need less samples to do things well. Now, one of the ways that we can actually affect the precision of measurements is by taking the right number of sig figs from our instruments. So we're always going to take the last digit reported, and that's going to be our estimated digit, and our only estimated digit. So any place that we can estimate accurately, we're going to estimate one digit. So example here, we have a graduated cylinder. We see that there are demarcations at each 1/10 of a milliliter, but then we can actually estimate in between here. So we might say, okay, this meniscus is just above the third line, so we know that there's 10 because we see the 10 marking down here. Oh, not 10. We know that it's 9 because we're actually marking the opposite direction. 9. And then we have 1, 2, 3, 4, 5, 6, 7, but we're just above that 7 mark, so it will be 9.6, and I think it's probably 9.69, estimating that last digit. So this last digit is the estimated digit, and we're only going to include one estimated digit. It wouldn't be accurate to include more than that. With a scale, the estimated digit is always the last digit automatically, so you should always record the complete reading of the scale. With a graduated cylinder or a ruler, the estimated digit is always going to be one past the level that the scale is marked off. So we end up having markings at the tenths unit. We end up having sig figs going to the hundredths unit. This allows us to have more precision in all of our measurements, and allows us then to be able to reduce our standard error of the mean, get more accurate representations of the total. Whenever we have significant figures in our samples, we need to know how to deal with them if we are going to make multiple measurements and we have to deal with propagating those. So say we measure out that 9.69 milliliters now, and then we add out another 1.00 milliliters, we need to know how many decimal points we're going to keep. It's going to depend on the type of operation, but we're always going to be limited by the measurement with the least precision. In addition and subtraction, we're always going to preserve the lowest level of precision relative to the decimal. So if our lowest level of precision is the tenths place, we're going to stop things at the tenths place. If our lowest level of precision is the hundreds unit, we're going to stop things at the hundreds unit. So in order for us to do addition and subtraction well, we really need to get things into the same scientific notation so that we can scale this properly. If we do multiplication and division, we're going to preserve the lowest number of sig figs. So this is actually a lot easier. If you have 3 sig figs and 4 sig figs, you keep 3. If you have 5 and 2, you keep 2. You always keep the lower number of sig figs. In logarithms, this is probably a new rule for you. The number of sig figs that are on the log side is going to be equal to the number of sig figs in the mantissa. That's the places after the decimal. So if you have 3 things on the log side, then you're going to have 3 things after the decimal. The thing before the decimal is called the characteristic, and that doesn't count. Your textbook doesn't talk about this, but this is actually fairly important. Whenever we're reading data from graphs, we want to make sure that we pay attention to how much accuracy can be or how much precision can be gleaned from the graph, and that's going to be dependent on the demarcations. So if we look at the graph up here on the top left, we see that the demarcations are only at the tenths unit, whereas the demarcations here are at the hundredths unit. So we can read off a lot more precision in the bottom right, and so we can read the data much better. This one in the top left might be useful for showing trends or showing curves, but this one in the top right is going to be much better if we want to actually use data from the chart. Let's circle back now and talk about absolute error and relative error, or absolute and relative uncertainty, which were measurements that on an individual basis we use to talk about error from the mean, or systematic error, on a cumulative basis, we can actually use those to talk about the random error as well. So whenever we have absolute error, it's going to be the values minus the accepted value, and relative error is going to be that absolute error divided by the mean value. We can now use those to report expected range for our value. So we might say this is our accepted value, but we know that we have some error in that value, so we're going to say that it's within it's 5.0 mils within 0.1 mils. So that would be a metric that's reporting absolute error, because notice the units are the same, 5.0 mils here, 0.1 mils here. We could also report errors in relative sense. So you might say we have a value of 47.5 micrometers, but we have some error associated with it, and it's about 7% error. If we wanted to get back into absolute error, we'd take the 7% and multiply it by 47.5 micrometers, and that would allow us to have our absolute error. Of course, if we wanted to go the other way, we take our absolute error and divide it by this 5.0, the 0.1 milliliters divided by 5.0 mils, and that tells us what our relative error is. It's very easy to convert back in between these. And notice that we always report these as 1 sig fig. So we're not going to have a 5.0 milliliter measurement and then say that we have 0.1000 milliliters of uncertainty. We don't have that much that precision in the mean, so of course we're not going to have that in the uncertainty. Likewise, if we said that we have 5.0 milliliters of uncertainty, or of sample, and we have 1.0 milliliters of uncertainty, we wouldn't really want that decimal place in either of those, because there's too much uncertainty to say anything about that decimal place if you could have a plus or minus 1 value. So we're always going to make sure that we have just 1 sig fig, and that sig fig is going to match up with the last reported sig fig in the actual value. Now, if we have uncertainty, and then we do calculations with that, say we have an uncertainty in mass and uncertainty in volume, we need to be able to deal with those uncertainties in the actual calculated value. We can only do this if we're only dealing with random error. Uncertainties from systematic error are going to be problematic in a very different way. So if we have only random error, each value is going to have an uncertainty, so every time we add those up, we're going to produce more uncertainty, because we could have things that are additive. We could have error that's higher coupled with another error that's higher, or we could have things that are subtractive. Both of those errors go the opposite direction, or they of each other, and so then we are going to end up with a lot more possible values, and we're going to end up increasing our certainties. But it's not linear. We're always going to increase our uncertainties with addition or subtraction as the square root of the sum of squares of absolute uncertainty. So another way of thinking about this is if we have a y value that's coming from adding or subtracting 3 different values, we're going to take the standard deviations, or the uncertainties of each of those values, we're going to square them and add them together, and then we're going to take the square root of that to get the actual error in our y value. So they're all going to add up the errors, whether we add or subtract them, but then they're not going to be completely additive, because we take the sum of the squares and then take the square root of that to get our standard error of y. If we do multiplication or division, we're not actually dealing with just the errors themselves. In absolute terms, we're dealing with relative errors. So instead of taking the square root of the sum of squares of absolute uncertainty, we're going to take it of relative uncertainty. So how does this work out practically? If we have a type of addition and multiplication and division calculation, we can have the relative uncertainties are each going to be the standard deviation over the actual value. So we'd say the relative uncertainty in A squared plus the relative uncertainty in B squared plus the relative uncertainty in C squared are going to be equal to the relative uncertainty in Y squared as well. So functionally, this is really complicated once we start to do combinations of addition and subtraction. We need to propagate these in order of operation. So if we do addition first, we'll propagate the uncertainty that way. Then we'll have to convert it to relative uncertainty to do multiplication and division. And we might have to convert it back if we have another type of calculation. Typically, To try to deal with some of these complexities, we're just going to keep all the extra digits until the end, so we don't end up introducing more error by rounding. Sometimes when we are marking things off along our way for calculations, we're going to keep what are called insignificant digits in our notebooks or in our records, just to make sure that we don't lose any of that data before we need to report our uncertainty in our final value. So this is often denoted by putting insignificant digits, digits that are only there for calculations and will be rounded off eventually, as subscripts. So here we have 5.0159 milliliters. The 5.9 are carried along for calculation but are not significant. Now, there are a lot of different rules for uncertainty. Obviously, we went over the addition and subtraction and the multiplication and division. This table sums up all of those. Typically, whenever we're doing something besides addition and subtraction, we're dealing with relative uncertainty. If we're dealing with power functions, we actually have a lot more complex rules. So one type of power function is y equals xa. Then the uncertainty is going to be in x. And we can actually just express the percent error or the relative error in y equal to the power that we're raising x to times the percent error in x. It's a fairly straightforward type of calculation. If instead we have the uncertainty in the exponent, now we have to deal with a lot more complexity. The relative uncertainty of y has to be related to the absolute uncertainty of x. So we have, this is going to be the absolute uncertainty, this would be the relative uncertainty, and we'd end up having those related via a log function of a. If you want a complete list of rules for logs, these are not something I'm expecting you to memorize, but are something that might be an easy way for you to look up how to deal with this if you have a power function as part of your calculation. We also need to talk about how we need to round uncertainty. So to illustrate this point, I put up a calculation. You have y equals 5.0 plus or minus 0.9, plus 2.5, plus or minus 0.9, minus 15, plus or minus 2. Now, we could probably see right away that 5 plus 2.5 is 7.5. When we minus 15, it's negative 7.5. We have to round this. So generally, we round things that are last digit 5 to the nearest even number, because that helps us to reduce bias. That way we're not always rounding up. So we'd say that we're going to call this value negative 8. So y equals negative 8. That's great, but how do we deal with that error? We know that we can take the standard error of y, or the standard deviation of y, and set it as equal to each of these reported values squared, and then take the square root to get this standard deviation. So we know that we'd end up with 2.37 for that value. You can calculate it out for yourself if you don't trust me. So then we'd say that y equals negative 8 plus or minus 2.37. Well, that doesn't make any sense because we don't know y to this many significant figures. If we say that we only know y to minus 8, then it's useless to give an additional 2 sig figures. So what we should actually report is y equals negative 8, and then we'd say plus or minus 2. All right, we want to round off these last 2 digits. Those are no good for us. Just scribble them way out there. We want to make sure that our last digit in our known value, in our y value here, is going to be the same as the last digit in our uncertainty. We could also report as a relative uncertainty with just 1 decimal place. That would also be acceptable. Hopefully this gives you a better idea of how we deal with uncertainty in our measurements. You'll find the problems for this chapter posted at the end of the Moodle section.